Welcome back, everyone. Ready to dive into a topic that's going to leave you completely mind blown.
I hope so. This one's a wild ride.
We're talking quantum computing today, and I gotta say, just wrapping my head around it has been a trip.
Right. It's like peeking into the future.
It really is. Imagine a computer solving problems in minutes. Problems that would take even the most powerful computers we have now, like billions of years to figure out.
It's not even just about speed, though, right? It's a whole different way of thinking about computing, like completely different rules.
Okay, so let's break that down, because I think a lot of people hear quantum computing and think, oh, it's just like a faster computer, right? But it's so much weirder and more complicated than that.
Way weirder. It's like the difference between, I don't know, riding a bike and teleporting. We're not just improving transportation, we're breaking the laws of physics as we know it.
And it all comes down to this thing called quantum mechanics, right? Which, let's be honest, sounds pretty intimidating.
Yeah, it's got that whole science fiction ring to it, but trust me, it's worth trying to understand at least the basics.
Absolutely. So, like, quantum mechanics in a nutshell.
Okay, so in our everyday world, we're used to things being one way or the other. Lights on or off, the cat's in or out, basic stuff.
Makes sense.
But in the quantum world, things get fuzzy. It's like, at the tiniest level, particles can be in multiple states at the same time.
Whoa, okay, my brain just glitched a little. Multiple states at once.
It's like that thought experiment, Schrodinger's cat. You've heard of that one, right?
Vaguely. The one with the cat in the box, right? And it's both alive and...
Exactly. It's both alive and dead until you open the box and look. It's all about this idea of superposition, where things can exist in multiple possibilities simultaneously.
Okay, that one's always messed me up. I can kind of picture it with, like, okay, imagine spinning a coin. It's both heads and tails until it lands, right?
Yeah.
But how does that actually work in a computer?
It all starts with the qubit. Think of it like the building block of quantum information.
Like a bit, but quantum.
Exactly. But here's the cool part. Because of this whole superposition thing, a qubit can be both 0 and 1 at the same time.
Hold up, both at the same time. So it's like that spinning coin, but it's storing information.
You got it. It's mind-blowing.
Right, no kidding. So instead of just ones and zeros, we've got this whole spectrum of possibilities. And that's what makes quantum computers so powerful.
Exactly. They can explore tons of solutions all at the same time, instead of having to go one by one like a regular computer.
Okay, so we've got these qubits, each one a spinning coin of quantum information. But how do we actually control them, get them to do something useful?
That's where quantum gates come in. They're like the instructions we give to the qubits.
So instead of just flipping a switch on or off, we can tell these qubits to do what? Spin faster, change direction, something like that?
Kind of. Imagine it like, you know how in regular computers we have logic gates, those AND or not tick gates?
Yeah, those are what control the flow of information.
Yeah.
Right?
Exactly. Quantum gates are similar, but instead of just working with zeros and ones, they manipulate these qubits that are in multiple states at once.
Okay, so it's like a whole other level of logic gates working with these quantum rules we were talking about.
You got it. They're the tools we use to interact with and manipulate these qubits, to actually do computations.
So we're like choreographing a dance for these qubits, with each quantum gate being a different step or move.
I like that. A quantum dance. And just like a complex dance routine, you need the right choreography to get something impressive, right?
Makes sense. So that's where these quantum algorithms come in.
Exactly. They're like the whole choreography, the entire sequence of quantum gates that tells the computer what to do, how to solve a specific problem.
And we were talking about one specific algorithm earlier, Shor's algorithm. That was a big deal, right?
Huge. It's one of the reasons there's so much buzz and some concern around quantum computing.
Because it can break encryption. I feel like we got to unpack that, because that's kind of scary stuff.
Definitely. So right now, a lot of our online security, everything from banking to government secrets, relies on encryption that would take classical computers, even the super fast ones, like billions of years to crack.
It's like the ultimate digital lock, right?
Pretty much. But Shor's algorithm, running on a powerful enough quantum computer, could potentially break those codes in a much, much shorter time frame.
Like how much shorter?
We're talking potentially hours, days, maybe weeks, depending on the complexity. It's a whole different ballgame.
Wow. Okay, so suddenly all our digital secrets aren't so secret anymore. I get why people are kind of freaking out about that.
And it's not just about breaking codes. There are other quantum algorithms being developed that could revolutionize fields like medicine, material science, artificial intelligence, all sorts of things.
Okay, so less scary, more like potentially world-changing good stuff, too.
Exactly. It's a tool, and like any tool, it can be used for good or for, well, not so good.
Right. But before we get too carried away with all the amazing possibilities, let's be real. Building these quantum computers is no walk in the park, right? I mean, this is like manipulating the fabric of reality kind of stuff.
It's definitely not easy. It's one of the biggest challenges we face, like trying to build a house of cards in a hurricane.
Sounds stable. So what are some of the biggest roadblocks? What's making this quantum construction so tricky? So what are some of the biggest roadblocks? What's making this quantum construction so tricky?
Well, one of the biggest challenges is something called decoherence. It's kind of like, remember how we talked about qubits being in multiple states at once?
Yeah, the whole spinning coin thing, super fragile.
Exactly. Decoherence is what happens when those qubits, well, they lose their quantumness. They collapse into just a regular old 0 or 1.
So like the coin stops spinning and lands on one side.
Exactly. And it can happen really easily too. Even the tiniest vibrations, temperature changes, stray electromagnetic fields, any kind of environmental interference can mess things up.
Wow, so it's like trying to build a supercomputer in a room full of screaming toddlers, basically. That does not sound easy.
Yeah, it's a huge engineering challenge. And then on top of that, you've got the problem of scalability. Well, to solve those really complex real-world problems we were talking about, you don't just need a handful of these qubits. You need tons of them, thousands, maybe even millions, all working together perfectly.
Okay, so now it's like a room full of toddlers, and we're trying to teach them all to do synchronized swimming or something.
Something like that. It's incredibly difficult to build and control these systems at that scale, especially while keeping them stable and isolated from all that potential interference.
So yeah, definitely not easy. But people are working on it, right? Like, we're not just going to give up and go back to our regular old computers.
Oh, absolutely not. The progress being made in quantum computing is incredible. Like, every day there are new breakthroughs, new techniques being developed. It's a super exciting time to be in the field.
So it's more like a work in progress than a pipe dream.
Exactly. Think of it like, where were we with classical computers back in the 50s? Big, clunky machines, took up entire rooms, not exactly user-friendly.
And now I can practically fit a supercomputer in my pocket. Kind of. So are we saying quantum computers are going to be in our pockets someday?
Maybe not our pockets, but the point is the technology is advancing rapidly. It's not a matter of if, but when.
And in the meantime, researchers are exploring all these different ways to build these quantum computers. We saw some articles about superconducting qubits, trapped ions, things like that. It's like everyone's trying to find the best recipe.
It's like a quantum cooking show, right? But yeah, different approaches have different pros and cons, and it's not clear yet which one is going to win out in the long run.
So lots of competition, lots of innovation. Sounds like the future of computing is going to be pretty wild. But we're not just talking about faster computers here, are we? This is like a whole new paradigm shift in how we solve problems.
Absolutely. It's not just about doing things faster, it's about doing things that were literally impossible before.
We talked about breaking encryption, which is kind of scary, but also there's the potential for good, right? Like curing diseases, designing new materials, even understanding the universe in a whole new way.
Exactly. Quantum computing has the potential to revolutionize pretty much every aspect of our lives, and we're just getting started.
Okay, so maybe I lied. My brain is officially broken now, but in a good way, I think. This has been an incredible deep dive, and I'm both excited and terrified to see where this technology takes us.
Me too! It's the kind of field that keeps you up at night, wondering about all the possibilities.
Well, listeners, if you're not already fascinated by quantum computing, I don't know what to tell you. Go do some more research and prepare to have your mind blown. This is The Deep Dive, signing off, and may your future be quantum.